Okay, so we are going to look at daily practice two-dimensional motion problem C. This problem reads, we were driving by the St. Paul Ski Jump Club on the way to my daughter's food allergy walk. One of the runs, the jumpers go off purely horizontally. The jump is 25 meters high. If they land 35 meters in front of the jump, how fast were they leaving when they left the jump? All right, let's look at it. So, what is my object of interest? Well, I'm interested in analyzing the skier. So my object of interest is the skier. Then we want to identify when the motion starts and when the motion ends. What begins my motion starts that stopwatch, what ends my motion ends that stopwatch. So we're interested in when the jumper goes off the ski jump and lands in the snow. All right, so what type of problem is this? One dimension or two dimension? Well, it's two dimension. He's going to travel both away from the jump and down when he lands. And of course, if he's flying through the air, that problem can be identified as free fall. So let's define our world. Here's the jump. Here's sort of that horizontal end of the jump. And the skier, there he is, he's crazy hats again, is going to go off the end of that jump. His legs are crazy, but he's going off purely horizontally. We know he's going to land somewhere over here, and it tells us that he lands at a very specific distance away from the jump. So there's our picture. Now we have to identify the world. Split the world into horizontals and verticals. So where will be our horizontal origin? Well, let's set our horizontal origin right at the location of the jump. So if this is our origin, anything to the right is positive, anything to the left is negative. Now we're told that he lands 35 meters in front of the jump. So if he lands over here, that horizontal position is going to be a positive 35 meters. All right, now let's divide the world vertically. Well, let's say that our ground, I'm going to do this one a little bit different than we've been in the past. Our ground is at our vertical position equal to 0. Well, if we know that the jump is located 25, I think was the number, 25 meters high, we know our vertical position at the end of the jump is at a positive 25 meters. 25 meters above the origin. Everything up is positive. Everything below that ground level is negative. All right, so two dimensions, two origins, two lists. We have our horizontal list. And so let's look at those values. Where does the object start horizontally? The skier. Where does the skier end horizontal? How fast are they going horizontally to begin with? How fast are they going horizontally to end with? What is that acceleration horizontally? And the time, which of course is the same horizontal or vertical. So let's look at that horizontal list. Pause the video if you're tempted and try that list and then see how you do with it. All right, where does he start horizontally? Well, I set the origin at the location of the end of the jump. I want to know when he goes off the jump, so he starts at 0 meters. We know he stands 35 meters in front of the jump, so our final horizontal position when he lands in the snow is 35 meters. And again, it's positive. It's to the right of the origin. How fast is he going? Well, that one's not answered for us in the problem. It's not given, so we don't know his initial horizontal velocity. His final horizontal velocity is also not given, so we don't know that. But we do know in the horizontal direction there's nothing influencing the motion. There's no change in motion. So his acceleration must be 0 meters per second, which does tell us that these two will be the same when we look at the analysis. Time, we're not so sure. Not given in the problem. All right, there's our horizontal list. That defines what happens horizontally. Well, let's look at also what happens vertically. So, same players. Positions at the beginning of the motion, position at the final of the motion. Velocity at the beginning of the motion, it's not horizontal, vertical. Velocity at the beginning of the motion vertically, velocity at the final motion vertically. Acceleration vertically and time, again, is independent of direction. All right, my initial position vertically. Well, when we set the origin here at the snow level, the base, he starts 25 meters above it. So it's positive, and it's a positive 25. He ends on the snow, which we defined as the origin. The problem says he goes purely horizontally off the jump. Well, if he's purely horizontal, there's no motion in the vertical direction to begin with, but we know he starts to fall down. So he's going to have a final velocity when he hits the snow vertically, but we don't know what that is. Because of this free fall idea, and we know that the acceleration is that which is due to gravity, so 9.8 meters per second squared, and we don't know the time. All right, so the problem wants to know how fast is he going when he takes off that jump. Well, we know he's not going at all vertically, so how fast he's going must be related to the horizontal motion. So we can use the horizontal motion to look at that. We're interested in that initial velocity horizontal. Also happens to be the final velocity horizontal. Now, initial velocity is in two equations, the position and the velocity equation. But because the acceleration is 0, our velocity equation is only going to tell us that the initial is equal to the final, which I already know. It's not going to tell us what it is. So let's use the position equation. So x final is equal to x initial plus v initial t plus 1/2 at squared. Again, we're interested in this in the horizontal direction. X final is 35, x initial 0. We do not know the initial horizontal velocity. We don't know the time either. Plus 1/2, 0 times the time squared. So that goes away. We're left with 35 is equal to v initial horizontal times time. In order for us to determine that initial velocity, I need time. So again, as we seem to be the case in a lot of these problems, I need to find time. So time becomes a variable of interest. Now, we've already exhausted what's usable in our horizontal dimension, but time's also in the vertical. So again, we look for that time being in both and understanding where do we see more of the other variables we know. Again, that will be in our position equation. This will be a very powerful equation to use most of the time, but it's always important to assess if it's the appropriate one. Do I have enough variables in it? All right, so x final is 0. X initial is 25. These are our initial positions in the vertical dimension. Plus an initial velocity of 0 times time plus 1/2 negative 9.8 times my time squared. And I'm going after that time value. So I end up bringing 25 to this side. Negative 25 equals negative 4.9 times my time squared. And solving that, I get a time equal to 2.26 seconds. All right, so there's my time. That goes in both lists. I use a different color to help distinguish that I calculated it. And now that I have time, I can certainly finish my problem. So 35 is equal to v initial horizontal, the thing I was interested in, times my time of 2.26. Solving for v initial horizontal, I find that he was traveling 15.5 meters per second in order to make it 35 meters in a 25-meter jump. Does that make sense? Well, we know he's got to be moving. When he leaves that jump, he's moving. And we know based on how I've drawn the problem and I've identified the direction of his motion, it needs to be positive. So it's not unreasonable that we have a positive non-zero value. All right. Again, with two-dimensional motion, we conceptualize the problem the same way we've always been, identifying that object, really focusing on what is that motion, what begins it, what ends it, and then that's all I care about. Recognizing we have two dimensions, which for us means free fall. Then we draw our picture, and everything doubles. Two origins, one for the vertical, one for the horizontal. A horizontal descriptor of motion, a vertical descriptor of motion. Independence is so powerful for two-dimensional motion analysis. really recognizing what we are interested in solving for. We're interested in solving for that velocity off the jump. We go after that velocity. It tells us what we need. We reevaluate, recognizing where we can get that information and then using it. Great job.